All right, so if a reaction stops advancing, it's because the G stopped decreasing. The Gibbs free energy stopped decreasing. So at this point, well, what must be true is that G must be at a minimum. Because if to go forward would decrease G, it would be going forward. And we know that it just came from backward, right? It just came from where there were more reactants. And we know that it went forward from there. So we know it was on the way down, and now it's stopped decreasing. So the free energy, the Gibbs free energy, must be at a minimum. So what must be true at that point is that the derivative of G with respect to the moles of A, right? The moles of A being the amount of reactant, that must be equal to 0, okay? Because we know that functions are at a minimum when their derivatives are 0. And actually, this happens, and I'm not proving it here to you, I'm just telling you, I'm sort of giving you the previews of coming attractions. This happens when mu B and mu A become equal. And so what I'm going to do now, is basically show you this mathematically. I need to prove this, which is not so hard in this simple case, really. But I want to go back and I want to write the expression for dG. And see how it relates to mu A and mu B, and get to this point where these two things come out to be equal. So I'm going to do that by starting by saying that the Gibbs function is a function of temperature, pressure, and in this case, there are only two things that are important beyond that, and that is the moles of the reactants and the moles of the product. So it depends on 4 variables in this problem, in this situation. Okay. So that means that dG, the total differential, is equal to, okay, so now here's where I exercise what we learned about at the very beginning of the semester. dG dt plus dG dP plus dG dNA plus dG dNB dNB. So I haven't written anything earth-shattering here. This is like writing that if f is a function of x, y, and z, df is df dx dx plus df dy dy plus df dz dz. All right, but now what I want to do is I want to write this a little simpler. So I have dG dt plus dG dP dP, and now I'm going to call this this is the sum of dG dNi dNi, right? So summing over all the moles of reactants and products. So we can use this further later on when we have more of them, but right now we only have the 2. So now we have to say, okay, let's do something. Let's say, what if pressure and temperature are constant? Then we get to get rid of both of these terms, right? They just go away. And we end up with that total differential dG is the sum of dG dNi, how G changes with the moles of each one of those players in the reaction, times the change in the mole of that player, that reactant or that product. All right, so this equation right here, this is how physical chemists start to talk about chemical equilibrium, right? This is really a starting point. Okay. So if we have our reaction like this, and we have this, if we apply this, that means that dg, write this black better, I can see it better. dg is, okay, so this is dg dNA times the moles of A, change in moles of A, plus the derivative with respect to NB times dNB. And let's not forget now that this is mu A. Okay, that is how the Gibbs energy changes with the moles of A. So we have this. And now if we consider this simple reaction and we think about the change in moles of A and the change in moles of B, what do you know about the change in moles of A and the change in moles of B? Are they really independent? These are related, right? Especially in a reaction as simple as this one, right? Whatever mole of A is lost, well, that many moles of B was that's how much B increased by. So really, the change in moles of B is the negative of the change in moles of A. And we're just going to call this dx, okay? And we say that this x is the extent of reaction parameter. And x starts at the beginning of reaction at 0 when you have all A, and goes until it's equal to 1. It goes from 0 to 1 when you're at all B. I'll talk more of that extent of reaction parameter. Well, I'm actually going to continue to talk more even now, but so here we have a pretty easy situation. All right, we said that that the partial pressure of A starts at 1, and if the reaction goes to completion, it would be equal to 0 at the end. And of course, since A always gives you a B, you would start with a 0 as the partial pressure of B, and you would end up with 1 as the final pressure of B. So here it's very simple. You know, if you just think of the extent of reaction parameter as being, if you think of that extent of reaction parameter as just being the partial pressure of B with no units, it kind of works here, okay? But I just want to, before I go into getting more into this example, hold on a minute, I'm looking for something. Yeah, I'll go. So what I wanted to tell you first is, like, what if, so this is kind of an aside. What if the stoichiometry isn't this nice? Where you just have everything is 1 to 1, okay? So suppose you had this as a reaction. 2A goes to, let's say 3A, that's what I have here. 3A goes to 2B plus C. Okay, so how would we define the extent of reaction parameter here? So this is what you would do, and I'm going to tell you, then I'm going to tell you why. We would say that the change in the extent of reaction is the same as the change in the moles of C. That's because C has a stoichiometric coefficient of 1. And at the beginning of this reaction, you would have 0 moles of C. So anyway, dx would be dNC, which would be the change in moles of B divided by 2. And it would also equal the change in moles of A divided by 3 with a negative sign. So what we're going to do is we're going to put all the different reactants and products on equal footing. And this is kind of like what you do in freshman chem when you talk about kinetics. But anyway, anything that has a stoichiometric coefficient, you simply divide the change in the moles of that by its stoichiometric coefficient. This would be, say, divided by 1, right? And anything that's a reactant is going to get a negative sign in front of it to put it on equal footing with the formation of a product, because reactants are going away and products are coming in. And so here I could say that, you know, two of these form for every C that forms. So you would have to divide the change in moles of B by 2 to get the change in moles of the change in the extent of reaction. To put everything on equal footing here, you would have to divide by 3 because the moles of A are going away at, you know, with 3 of them for every time a mole of C forms. So to put the moles of C change on the same footing with the change in moles of A, not only do you have to put a 3 here, but you also have to put a negative sign. So it's very simple what you have to do in these types of problems. You use a negative sign for reactants, and you divide by the stoichiometric coefficient. If you don't have anything with a coefficient of 1, then everything gets divided by the stoichiometric coefficient, and you still succeeded in writing a dx that puts that if it equals all these type of things, that everything is put on equal footing. So so that's how it's defined, and that's the way we use it. So if we go back to the simple example that we're working on, and we say dNB equals dx, which is minus dNA, and we had mu A times the change in moles of A plus mu B times the change in moles of B is equal to dG, change in the Gibbs function. Okay, and I substitute in, what I end up with is mu A times minus dx plus mu B times dx, okay, equals dG. So this becomes, if I take out the dx, mu B minus mu A dx. And then I can do something even better, because remember, this x is what we call the extent of reaction parameter, okay? And it's very cleverly defined so that it goes from 0 to 1. 0 at the beginning of a reaction, 1 at the end. But now what I can do is write an actual derivative. The change in the Gibbs function with respect to the extent of reaction, with respect to how far the reaction has gone, given the definition I told you about, is equal to this difference for the A to B reaction. This is pretty cool, you know? This is how the Gibbs function changes with respect to extent of reaction. So where is equilibrium? If we go back to this question, where is equilibrium? Remember, we talked about how G is changing over the course of the reaction. We know G has to be decreasing because we know by the second law that for a reaction to be spontaneous, G is decreasing. So where is equilibrium? Well, if the reaction stops going forward, it means that to go any further forward, it would actually have that G would be going up. That's why it's not going any further. So it must be at a minimum, okay? So equilibrium is when this derivative equals 0. And G is at a minimum. Okay. So this thing here, this fantastic derivative, okay, dg dx, this actually tells what direction the reaction will go in. So I said when you get to equilibrium that this derivative equals 0, but that's only one point. What is it before equilibrium on the reactant side? What is it on the other side? What if you started with all products? So here's a very simple answer to that question. If the derivative of G with respect to the extent of reaction is positive, okay, that means that the slope of G versus X, because that's what the derivative is positive. Now, I don't have to know anything about what that looks like. I'm going to show you what it looks like later, but I don't have to know anything about the shape of G versus X to know that at some point it has a positive slope like that. Okay, and if that slope is positive for G versus X, then which way is this reaction going to go? Well, if you increase X, what's going to happen to G if the slope is positive? If you increase X, then G does what? If the slope is positive, then increasing X leads to a G that's higher. So by the second law, what's actually going to happen here? If X increases, G increases. If X decreases, G decreases. Well, that's what's going to happen because G is going to decrease. This happens spontaneously. The reaction is going to go that way. It's going to go in reverse. When this derivative is positive. Okay, it follows a downward, it's always going to go down. So it's going to go whichever direction it needs to, that gives free energy to go down, because that's the second law. That's what's going to happen spontaneously. And then I'm just going to write the opposite thing. If dg dx is negative, okay, then the slope of G versus X is negative. So if I have a graph of Gibbs function versus X, slope is negative. So now if X increases, if the reaction goes to the right, that's what increasing X means, then G decreases. And so by the second law, that will happen. Because we've used the second law to show that the Gibbs free energy has to decrease. And the reaction will go in a direction that decreases G, so the reaction will go forward. Okay. So for our A-B reaction, just at the beginning, we said the partial pressure of A is 1 and the partial pressure of B is 0. So we have formulas. We know that mu A is mu A 0 plus RT log of PA. And so if PA is 1, then we know this term is 0. So mu A is mu A 0. Mu B is mu B 0 plus RT log of PB, but this is 0, right? So the log of 0 is negative infinity, right? So it's very, very low. So you could see here that mu A is greater than mu B. So dg dx which is equal to mu B minus mu A, which we showed a little earlier. All right, going back a little bit, see right here, mu B minus mu A. So at the beginning, that's what we're talking about. This mu B minus mu A is negative. So the reaction goes forward to decrease G. Okay, suppose we started at the end. Suppose we have all B instead of all A, okay? So our PB is equal to 1 and PA is equal to 0. Well, then we have the opposite situation, right? Then our mu B is going to be mu B 0 plus RT log of PB, and this is going to be the log of 1, so this is 0, so mu B is mu B 0, that's fine. Then we have mu A with the same equation, but now PA is equal to 0, so this is negative infinity. So at the beginning, at the very end, with all products, we have that mu B is greater than mu A. So mu B minus mu A is positive. That's the slope. Oops, that's the slope. So the reaction goes in reverse. And we know this is true. If you start with all reactants, the reaction's going to go forward. If you start with all products, the reaction's going to go backward. It really is, regardless of what the delta G0 is, which we're going to learn more about that very, very shortly. At some point in the middle, right, we're going to have the two being equal, and that is equilibrium. So somewhere in the middle, you get equilibrium. So this thing, this dg dx, Atkins has a special name for this, okay? And it's in, I think it might be chapter 7, or maybe we're in chapter 9 already. We just did a couple of little sections in chapter 5 last time, and then most of the rest of what we do is in chapter 9. But anyway, in there, this dg dx is called delta RG in Atkins. He calls it the reaction Gibbs function. I really just prefer calling it what it is. It's the change in the Gibbs free energy, the derivative of the Gibbs free energy with respect to the extent of the reaction. So what should G look like? If I was really going to draw a graph of the Gibbs free energy versus the extent of reaction, okay? So if I have all A, I'm going to have some value for this, what the Gibbs function is when it's all pure A. This is actually mu A 0. And then if I have all B, I'll have some different value. And now what happens during the reaction? Well, at the beginning, remember I went over this, right? At the beginning of the reaction, this derivative is going to be negative, and the reaction is going to go forward to decrease the Gibbs function. So, oops, geez, it's going to go down, and 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 it's going to go down. And then at some point, it stops going down. This is where dg dx is equal to 0. This is equilibrium. But on this side, dg dx is negative. the slope is negative. That's because mu A is greater than mu B, as I described. Now, if we started over here, well, we have mu B is greater than mu A. So the slope, which is mu B minus mu A, is positive. There we have a positive slope. That means the reaction is going to go that way. And it's going to go that way and that way and that way until it stops dropping. So you can approach this equilibrium from both sides. Okay. So what this is kind of a cartoon, right? I mean, I didn't prove anything here, but what I'm going to do now is I'm going to go back and take those equations that we had, right? That we had mu A is RT times the log of PA, and mu B is RT times the log of PB. And we know that the difference, mu B minus, actually I'd rather write this the other way with the B's on top, because I'm going to subtract them. Because I know my dg dx is mu B minus mu A. And that is, I forgot mu, oh God. Oh well, messed that up good. So I'll subtract them term by term. Okay. So first I'd like to tackle what this is, because this is something we really can understand. Mu B0 minus mu A0. Okay. This is basically the molar Gibbs free energy of B at a standard pressure of 1 bar minus the molar Gibbs free energy of A at a standard pressure of 1 bar. Okay, well, if I run the reaction, A goes to B at 1 bar, okay, then what is the delta G0 of that reaction? So run this reaction at standard pressure, okay, delta G0 for that reaction is simply mu B0 minus mu A0. So, so that's what this difference is. It's like the Gibbs energy of the final minus the initial. It's a final minus initial for the reaction run under standard conditions. So that's what this is. So this is delta G0 for the reaction. Well, that's nice because that's something that we can kind of understand. So we have the first thing there. We have that dg dx equals delta G0 for the reaction plus this crazy term here. Okay, and so this is really the fun part right here, to try to visualize what this looks like and help us understand what's happening to this slope as the reaction progresses. So I just want to go over how this is set up here, right? We have that our, well, okay, so first of all, yeah, the partial pressure of A, it starts at 1 bar. That's how we want to set this up. It ends up at 0 bar if it were to go to completion. Exactly the opposite for the partial pressure of B. Starts at 0 and goes to 1 bar. While at the same time, this extent of reaction thing starts at, it goes from 0 to 1 and it's unitless. So, so one thing that's certainly clear in this reaction is that the partial pressure of A is 1 minus the partial pressure of B. Oh, I forgot to tell you something. Yeah, this was it. Actually, I knew there was something I was missing here. And that is that this reaction, we're going to run the reaction at 1 bar pressure, so that the sum PA plus PB is equal to 1. Right, so that's why I'm able to do this. And once I can do that, I have that dg dx equals this delta G0 plus RT log of PB minus the log of 1 minus PB. So suddenly I have just one variable, and I can graph this thing and I could look at it. In fact, this actually is X, ln X minus ln 1 minus X, where X is the extent of reaction. Okay, so now what I want to do is show you what this looks like on a graph, because I think that all this is really very, very out there. And I think when, at least for me, when I look at a graph of something, it helps me understand. So what I want to do is start off by thinking about, I'm actually going to go to the next page. Just want to, does anybody need me to back up and copy anything down, or how's it going out there? No. All right. So let me go over here. All right, so if I just start by thinking about a log graph. So I showed you this before, but I'm going to show it to you again. So here, if I have the natural log of X versus X, and this is where the 1 is, that graph starts at -infinity and does this, and then crosses the axis at 1. This is what ln X looks like. And you can see that ln of 0 is equal to ln of 1 is 0. So what we do right here is we focus in on this part of the graph, just the part where the log is going from 0 to 1, basically, because that's what's happening to the extent of reaction. That's our X. X basically goes from 0 to 1. So this is where we're going to focus. Okay, so now what I've done is I've printed some of these graphs so that you can have a look at them. Okay, so this is just the plot that I just showed you, except it ends here at 1. Just like it's just looking at this part here, going right to here. So it's this part of the graph. Well, actually it goes down to 0, and this does a pretty good job showing the asymptotic behavior. Okay, so this is just the natural log of X. All right, if that's the natural log of X, then what's the natural log of 1 minus X? Well, if you take this thing and sort of flip it between the 0 and the 1, you get this curve right here. And this actually is the natural log of 1 minus X. So it's kind of like the flipped curve between 0 and 1. And then if you take the negative of that, you just flip it on the, whatever is negative, you make it positive, more negative, more positive. So you just flip it around the x-axis. So this dotted line here is a graph of the natural log of the negative of the natural log of 1 minus X. Okay, so what if we want to do what we need to do, which is we want RT times the log of PB minus RT times the log of 1 minus PB. Well, that's really RT log X minus RT log 1 minus X. So it's RT log X minus the log of 1 minus X. Right, here's the log of 1 minus X. Here's minus the log of 1 minus X. Well, what happens when we multiply by RT? All that does, it doesn't change the shape of these graphs at all. It just changes the scale. It doesn't change the shape, only changes the scale. So it looks exactly the same. RT log PB looks exactly the same as the log of X graph I showed you. And then these are the two graphs minus RT log PA, or minus RT log 1 minus PB. And this is what we got it from by flipping. Okay, so now what we want to do is we want to actually add this and this. We want to add these curves. So, no, not those two. Wait a minute. That's not the curves we want to add. We want to add this curve. This is RT log PB. We want to add this curve and this curve. So these are the two that we want to add. So I put them on the same graph, and that's what they look like. So when you add these two, you're basically adding them point by point, and you could see that right here, they're going to cancel out right in the middle, that you have just as much of a positive here as you have a negative. So that's why it goes through the 0 over there. And then this negative infinity down here, well, nothing you can do about that. It's going to be there, and the positive infinity here. So you get this really beautiful looking curve, I think, very nice looking curve. And what this is that big term, right? This is what it's dg dx is delta G0 plus RT times this crazy thing. And what I've graphed is this here. This is graphed. That's what that black line is. It doesn't include this part. It includes the interesting part, the thing that's happening, the rapidly changing part, not this constant part. Right? This is a constant. All right. So what you can see, it's very interesting here, is what this is. Don't forget, this is D. This is, okay. So let's consider a simple case. All right. Well, let's consider the simple case of a simple case when delta G0 for the reaction is equal to 0. Well, so that means that the free energy of the pure reactants and pure products under standard conditions would be exactly the same. So, that's not really all that unusual. There are some reactions that would have very tiny delta G's of reaction, like if you had like a cis-trans isomerization, that doesn't have a huge change in free energy, or maybe a N-butane, isobutane, isomerization, there wouldn't be a big delta G0. So if you had a reaction where the Gibbs free energy of reactants and products were the same, then this would be it. This would be dg dx, right? We would, if this were equal to 0, then this would actually be how the Gibbs function changes as a function of extent of reaction. So this would equal dg dx if delta G0 were equal to 0. And in that case, you could see, right, if this was dg dx, that here's a 0 here. This is where dg dx is equal to 0. And where does it happen? At x equals 0.5. So if you have a reactant and a product, and they have the same Gibbs free energy, then when you start with A and you end up with B, you're going to end up at equilibrium right in the middle. Okay. That's what this thing is telling you. And actually, we can analyze this even further. So so if we have this case, right? Okay, so we have dg dx because delta G is equal to 0. Okay, this is dg dx. This is at 0.5. So here's the 0. These are positive values of the slope, right? All these are positive values of the slope. And these are all negative values of the slope. Because this is the slope. This is the slope of G versus X. These are negative values of dg dx. Yeah, I'm not liking what I said here too much because I think I made it worse. So let me start again. Sorry. So if I want to figure out what does the Gibbs free energy look like, not just what the slope looks like, but what does the Gibbs free energy look like? So I have this nice graph. And this graph is dg dx provided delta G0 is equal to 0. But now I want to know, well, what does G look like? So how can I get at how to tell what G looks like? Well, it'd be nice to know what the slope is. I can sort of do that from the slope. So if I wanted to plot G of X, I need to use the fact that here dg dx is positive. And here dg dx is negative at values of 0.5 or less. And at values of 0.5 or more, it's positive, and it's equal to 0 at 0.5. So let's try and do a plot like that. So here, here I have the curve here, dg dx. This is assuming that this difference here is 0, mu b minus mu a is 0. So that's delta G0 equal to 0. Okay, and if this is what the slope is at every point, so here I know at 0.5, right in half of this graph, I have a minimum, I have a value of 0 for my slope. So whatever G looks like, it's going to have a minimum over here. It's going to be, going to be at some kind of a minimum there. But I know that at values of X greater than 0.5, these are all positive. So the slope will be positive on this side. And on this side, less than 0.5, these values are all negative, right? This is the 0. Positive is this way, negative is that way. So I'm going to have positive slopes on the right, and I'm going to have negative slopes on the left. And also you could see that when you have a value of X that's near 1, not only do you have a positive slope, but you have a really, really high positive slope. And that's because it approaches like this. Okay, so you have this big positive slope at the beginning. And then it gets less as these numbers come down, it gets less and less until it equals 0. And the same thing on the other side. You start off with this big negative slope. Way down here, you got a big negative slope. And so it's gonna big negative slope, and then gradually and gradually. So you have something that really looks like this. You have your equilibrium right here at the bottom. You have slope positive, slope negative. So what that tells you, since the slope is positive here, which way is the reaction going? It's going to the left. It's going the way to decrease the Gibbs free energy. And on this side, it's going the way to decrease the Gibbs free energy, which means it's going forward. So, so the conclusion here is that the equilibrium is at the halfway point. And but remember, this and this are at the same value, right? There is no delta G0 for the reaction. So when you start out, you have reactants and products, the same value of the Gibbs free energy, your minimum is going to be right in the center. There's nothing that's pulling the minimum to go one way or the other because there is no delta G0 in this reaction. So it's right at the halfway point. So at 0.2, which would be, let's see, this is about 0.25, so 0.2, the reaction is going forward. The slope is negative. Oh, sorry. Yeah, the slope is negative. Okay. If x is 0.5, the slope is equal to 0. This is equilibrium. It doesn't go either way. Oh, I should have written that next to 0.2. At 0.8, the slope is positive. Reactions going in reverse. Okay, so that's what you can get by looking at this graph. Now, that's the easy case. That's the boring case. Now what I get to do is figure out and show you what the effect of having a positive or a negative delta G0 is on this situation. So remember, we have dg dx is delta G0 plus RT log PB minus the log of 1 minus PB. Okay, and this is that crazy graph. So what happens when we add something to it? So we have this nice looking curve here. That's this part, right? But now let's suppose that delta G0 is positive. So what this means is that we're going to add a positive constant amount to every point on this curve. And so you're going to end up with something that looks like this. Just a lousy drawing. Okay, so you've raised this curve up. And look what happens when you do that, is that it crosses the 0, right? This is dg dx. This 0 is where equilibrium will be, because dg dx is 0 means you're at equilibrium. And you could see that the equilibrium will be on the reactant side. Well, when delta G0 reaction is positive, that means that G0 of the products is greater than G0 of the reactants. And so that's exerting an influence on where the equilibrium comes out. It's going to come out on the product side because the product side has a lower free energy. Okay, so the next set of graphs shows you this. So this is exactly what I just did. It says, okay, I'm adding this constant. This is delta G0 being added here at every point. And you could see that the new crossing point of the 0, this is where the thing that's being plotted, which is dg dx, is equal to 0, is over here. And that's something like, the way I've drawn it, it's about x equals 0.13 or so. So it's not at 0.5 anymore. So how can we understand this? How can we draw our G versus X curve? So this is if this were positive. So delta G0 is positive. Okay. So first of all, the first thing we have to realize is that now I'm not going to draw these at the same height anymore, because that's not true anymore. I have a positive delta G0. So that means that my reactants has a lower value of the free energy than the products do. So, so this difference here, that's the delta G0, and it's positive here. I see that I have my equilibrium much closer to the reactants. Let's put it right here. Here's equilibrium, let's say, okay? And that means I'm going to have a minimum there. All right. Now, between this point, 0.13, and the 0, I have negative, these are negative values of dg dx. So that means the slope is negative. When the slope is negative, what happens? So here, the slope is negative. So dg dx is negative. So that means the reaction is going to go forward to decrease the free energy. But on this side, all of these values, these are all positive. So that means that the slope here is positive. So that means that to decrease G, the reaction has to go backward. So if it were to have started over here, it'd be going this way. And so we have a curve that looks like this for the G. Okay. And equilibrium didn't come out too good, but it's right about there. So you can see that what's going on here is that the equilibrium will always lie on the side with the lower standard Gibbs energy when it's like pure A here, right? This is all A and this is all B. This is mu A 0, this is mu B 0. And so the delta G 0 is that difference. And we have a minimum. So the minimum, the equilibrium, is on the side of the reactants. And that's because the reactants have a lower mu 0. Okay. So now if you're at 0.05 over here, okay, the reaction goes to the right because that derivative is negative. Right here we have equilibrium. dg dx is equal to 0. And here, 0.5, like right here, dg dx is positive. Yeah, right, it's all positive, that's what this is. And so the reaction, so this goes left. Here, the reaction goes right. Oh, I wrote that down already. Okay. So that's the big reveal. Now, sometimes I ask students to draw a little sketch of the G versus X for the reaction. And there are some things that you could do that are absolutely wrong. All right. So I said that the minimum will always be on the side of the lower, the side, either reactants or products, whichever has the lower Gibbs energy when it's pure. So mu B 0 or mu A 0. So in this case, see, here's my minimum. It's on the side of the reactant or product. In this case, it's a reactant with the lower mu 0, right? Mu A 0, mu B 0, for example. Okay, so what if somebody drew this for a diagram? And this is possible to draw, but it makes absolutely no sense. So would you ever draw it like this? I mean, it's possible to make such a drawing. Here you have the minimum on the product side, but the reactants have the lower mu 0. So this is an impossible drawing. So don't ever give me a drawing like that. The minimum has to be on the side with the lower mu 0, the lower Gibbs function, if it was all pure substances. So don't give me a drawing like that. Never draw it like that. The minimum's on the wrong side there. And then finally there's the situation, the opposite situation, right? So this is what happens if delta G 0 is negative. So remember, it's mu B 0 minus mu A 0. What if it's negative? That means that mu B is greater than, wait, did I get that right? Yeah. smaller than mu A. Okay. So now we're actually adding, so dg dx is delta G0 plus RT and that whole big thing there. But now this is something that is negative. So it's being subtracted, right? It's something that's, it's causing dg dx to be a lower value than it would have been without it. Okay, so we're adding something negative here. So this curve is going down, it's dropping. And when it does, it intersects the 0 at a different spot, a spot at a higher extent of reaction. So now, first of all, we know that we have a situation like this. So now our mu B0 is smaller than mu A0. And we know our minimum is going to be somewhere on this side. And here it's telling us that the minimum is about at 0.9 or so for this, whatever parameters I picked for this one. So here I have, looks a little awkward. Well, maybe it's just hard to draw it that close. Whatever, there's my minimum. About 0.9. Okay, so here I have negative values of dg dx. So I'm going to have negative slopes. That means that this is going towards the products. It's going to the right. Here on the other side, I have a positive slope. Okay, so the reaction goes left. And here I have equilibrium. So, you could see that when you have a delta G0 that's negative, what we say in freshman chemistry, oh, the delta G0 is negative, the reaction goes forward. Well, you could see that it doesn't go forward everywhere, right? That it goes forward, but once you get particularly high values of the products, the reaction isn't really going forward anymore. It's going forward under standard conditions. What that's telling you is that standard conditions are somewhere over here where the reaction's going forward. But I think I've overloaded you guys enough today, so I'm going to stop. And we're going to pick up on this on Monday. Monday? Wow. Yeah, we're very close to the end of the material, and I'm gonna, well, it's not, yeah, there's always a few more things to do, but hoping to get to some problems. And if we have to meet on the 14th, it'll only be for problems. So we'll certainly be done by then. I haven't heard a peep out of anyone. But let me know how you're doing.
Seems to make sense.
Good. Yeah, look it over.
It's a lot to take in, but
yeah, I know.
It doesn't seem as confusing as some of the other stuff we've done.
Oh, that's good.
In my opinion, anyway.
That's okay. Yeah. All right. Well, I did post the solutions to assignment 4, a special problem. You might need to look at that for the quiz, by the way, if you didn't do that problem or if you did it wrong. Anyway, I gave that back today, so I'm not collecting that anymore. And I still have one, that delta G, the sign of delta S and delta H. I posted some scribbly answers to that as well. Yeah, that's all. I just did that today. I don't think there's anything else. I'm going to give you assignment 6, which is just a bunch of problems that involve this, but we really haven't done any of these problems yet. We're not sort of in a place yet where we can actually do problems. But you should be doing assignment 5, you should be able to do. Although I know you're working on the quiz and it's different material, but just to tell you, there's really only 3 problems on it, and 2 of them are, you know, what to do about extra work, and one of them is a heat engine problem. That's, I think, pretty easy. So anyway, that's all for today. I'll see you Monday, and if you have any questions about the quiz or anything, you want to talk about anything, please just send me an email. All right.
All right.
Okay, bye.